Alright guys, in this video we want to talk about how to compute the area of the region enclosed by a polar function. So the first thing I'm going to do is sketch a picture, and then we'll talk about exactly how we can write down an integral to compute the area for us. So I've drawn here what look like x and y axes, but this is going to be a polar curve, so this is more just for reference than anything else. But let's say we have a polar curve that starts maybe here and traces out something that doesn't necessarily look like a Cartesian function, although this looks a little vertical over here. So the idea here is then that this function is given by r equals rho of theta, so some function of theta. And at every value of theta, the function gives back a value of the radius r. Now what I want to do is the area enclosed by this curve now in the polar sense is the area that this region encloses between the points of the curve and the pole itself. Okay, so this is going to connect, the region is going to look like this. It's going to be bounded between the endpoints of the curve and the pole. It makes like what looks like a little triangle or a sector of a circle is the best way to think of it. But then the top is this different curve given by the function itself. And so what we want to do is try to compute the area of the region that's bounded inside of here. I'm not going to shade this in right now, but that's the idea. So again, this region is bounded between two specific values of theta. So let's say theta equals alpha and theta equals beta. Remember, theta equals a constant gives us these rays, the rays that emanate from the pole and go out into the plane. Okay, so to compute the area, we're going to do the same kind of thing that we did in Calc 1. We are going to take a partition of the theta interval. So we're going to take a partition that looks something like theta 0 equals alpha, which is less than theta 1, less than theta 2, and then build up until we get to some theta n, which is equal to beta. So we chop up our interval of thetas. These are the independent variables. And then we put those into the function, and this will chop up the curve into many pieces. And so I'll just draw a few dots here. I'll space them out so that we can see what's going on, but you can imagine that we're going to take this partition to have a lot of points, take n to be very big so that the points are very close together. And what we'll do next then is connect our pole to each one of these points. So we want to connect, like I said, connect all of these points from the partition with the pole, and then we'll choose one of these representative regions and try to compute the area that it's enclosed. So that's the idea. We first start by chopping up the interval. That's a partition. This should feel very familiar. We're just doing this with polar coordinates now instead of rectangular. But we take a partition, and then between two of these points, let's say that this one here is theta I, and this one over here is theta I plus 1. So I want to look at this particular sub-region and try to compute its area. And like I said, this looks like a sector of a circle. So I'm going to zoom in on this now, even though we're not done changing it over here. But what we want this to look like is a nice sector of a circle, because if we can write this as a sector of a circle where it has radius r and its angle is, I don't want to use the same letter, but let's say its angle is phi, then we know from geometry that the area of a sector of a circle is 1/2 times the radius squared times that angle phi. Okay, so we're going to try to use this formula for the area to help us compute the area of this shape over here. Now, we have the change in the angle all set. There's no problem there. We've already figured this out. The change in the angle here is what we'll call delta theta I. That's just the difference in these two theta values. So it's theta I plus 1 minus theta I. So that's the change in the angle itself. So that's what's going to take place of the phi in this formula that I just wrote down. The question, though, is what do we choose for the radius? Because as we go along this curve, the radius is changing. That's the whole idea. Our radius is a function of theta. It's changing from point to point. And you can probably guess that what we do is we choose any theta value that's between theta I and theta I plus 1. We choose a test point. So I'm going to draw the test point right there. But what we'll do is, we'll choose some theta I with a star that is in between, so such that this theta I with a star is between theta I It could be equal to them, but it's definitely not bigger. It's not outside of this interval. So this is our test point. And then we're going to use this theta I star to plug in and find our radius. And I already drew the point over here on the curve, so we can cap this off with a little cap of a circle here. And so we're going to say that our radius is equal to rho. Rho is our function, remember, of theta I with a star. And so this will go in for our r squared. Okay, and this theta I with a star could be any point. Obviously here it's going to make a big difference where we choose that point. But as we take, there's no surprise here, we're going to end up taking the limit. And when we take the limit, it's going to make these two rays of the theta come very close together, and it's not going to matter what we choose here. Okay, so let's write down an approximation here. The area enclosed by our curve is going to be approximately equal to the sum of the areas of all of these small partitions. All right, so it's going to be the sum, I from 1 to capital N, of our area formula. Our area formula is this, but it's with all of our relevant thetas and rhos plugged in. So it's going to be 1/2 times rho of theta I star, that's the test point, squared, that quantity squared, times the delta theta I. Okay, so what we worked out was the formula for the area of one slice, one sector here. We're going to add up all those sectors and we'll have approximately the area that we're looking for. Again, this is not good enough, right? We want the actual area. So without actually having to go through the whole Riemann sum argument, I think at this point in Calculus 2, we're all comfortable with the idea. What we're going to do is just we're going to allow n to get really big. We're going to take more and more and more and more partition points. That's going to squeeze them together and make delta theta I become very small. Okay? And so eventually what we get is this formula. So we end up with the area enclosed by the polar function. So the area enclosed by the polar function, r equals rho of theta. Rho is just a Greek letter for r. We use this in polar coordinates to represent the radius. The polar function, this is going to be given to us by area equals. The limit is capital N approaches infinity. Sum, I goes from 1 to capital N. 1/2 of rho of theta I star, quantity squared, times delta theta I. And of course, this just looks to us like an integral now, right? So this is the integral. Remember our boundaries in the theta direction were these green angles alpha and beta. So it's the integral from alpha to beta of 1/2 rho of theta, the function, quantity squared, times d theta. So this is our area integral in polar coordinates.